So let's wrap up section or chapter 2 on differentiation. We're doing related rate problems. So related rate problems are they are problems when we have more than one rate of change going on. And how does the change of one variable affect the change of another variable? So we're going to find out what these are and use these to solve problems. So we're going to start with a cone. So we have this cone filled with water draining out at the bottom. And we want to know, how does the volume change with time? We have the formula. If you don't remember it, fortunately I have it here. The volume of a cone is pi over 3 times r squared times h, where r is the radius of the cone, or radius of the base of the cone, and the height is the altitude of the cone. So we will use that formula to go through here. I gotta get this to pop up here. So what the problem is that as the water drips out, the height is changing, the radius is changing, and the volume is changing. So we have three things that are changing with respect to time. So this is where this implicit differentiation comes in. We're going to take the derivative, but notice we're taking the derivative with respect to t, and there are no t's in the problem. So we have to use the chain rule for everything. So the left side is easy, dv dt. Right side, we have a constant, we can pull it out, so we have to take the derivative of the r squared h. There we have two variables, and both of these are changing with time. If one of those was constant, we could pull it out with the constant, but the radius changes with time and the height changes with time, so we have to use the chain rule here. So we have r squared times dh dt plus h times 2r dr dt. And just kind of neatening it up a little bit, we got this. Here is our formula. If I want to know the change, how is the volume changing with respect to time, it depends on the rate of the height and the rate of the radius. And the problem is these are not constants in this problem, because if you know, with water draining out of the cone, as it gets lower, the radius is going to, they're going to both be changing at different rates. So with this problem, as I said, the change of the volume with respect to time is related to how the height of the water in the cone is changing with respect to time, and it is also related to how the radius of the base of that cone is changing. So these are what we call related rates. We need all of these rates involved to play with this problem. So that's where we're headed with this section. So let's actually see what this is going to look like. So we have x and y, and here we're not a situation. Y equals x squared plus 3. I want to find dy dt. I know when x equals 1, and I know dx dt when x equals 1. I have more things I need to find out. Because I want dy dt, I want a derivative, so I'm going to take my x squared plus 3 and do my implicit differentiation. So that's going to give me my dy dt. That's what I want. That's good. But derivative of x squared is going to be 2x dx dt. The derivative of 3 is just 0. But you notice, to do this, I need to know x, and I need to know dx dt. Well, we know x, and I know, and I know dx dt. I just realized that I have this worked out on this slide in the animation, and I didn't have to do this by hand, but we'll do it anyway. So I can plug those in to get 2 times 1 times 1 equals 2. So my dy dt is going to be 2. So now we'll take all of this out of here. And let's do it the way I originally designed this, which I had already forgotten. So we got the original equation, blah, 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 blah. Okay. So that's just what I did. This is a little neater way to look at it. Maybe easier to read than my chicken scratchings. This is the idea of a related rate problem. We do the implicit differentiation, but when we are plugging in, we have to know both a value and a rate of change. This is the idea of a related rate. The dy dt is related to dx dt. This one is not animated in here. I got to do this one by hand. Really, I do. Okay. Pebbles dropped in a pond. We make concentric circles. Outside is increasing at a constant rate of 1 foot per second. So this is a constant rate. That's kind of nice. When the radius is 4 feet, what is the rate of change of the total area? Because if you think about that, if the radius is increasing as the radius gets bigger, the area is going to increase faster and faster. But you think about that. You throw a pebble into the water, it is pretty much the radius increases at a constant rate. So we need to relate the radius to the area, and we know we have circles. So I'm going to start with the formula for the area of a circle is pi r squared. So now I'm going to come along and take my derivative. And again, I'm doing, most of these related rate problems are going to be finding the derivative with respect to time. Because we're talking about rates, we're talking about time generally. So dA dt, pi is a constant. R squared is what's changing, so that's going to be 2r dr dt. And now I need to plug in values. So I know the radius is 4 feet. I'll plug that in there. I know the radius is increasing. So right here, that's my dr dt. And I get pi times 2 times r times 1, or 8 pi, and I'm in feet per second. Feet squared per second, because I'm doing an area. I have r squared in there. Which is about 25.1, if you want to get an idea there. But it's important to note, it's only changing at 25 feet squared per second. The area is only changing at that rate when the radius is 4 feet. Once the radius gets bigger, this rate of change is also going to change. So the rate of change is dependent on the radius. Now this was a constant rate. That kind of helps us there. So here's your guidelines. And we don't always have to do all of this, but many of these are worthwhile doing. When you get a problem, first find out what's given. What are you given? What do you need to find? I like this idea of making a sketch and labeling quantities. Sometimes it's a lot easier if you can have a sketch to kind of see what's related to what. You don't always need to do the sketch, but that often will help you. Write an equation involving the variables whose rates of changes are given. You look at what are your variables involved, what have you been given, what do you need to find. If you can write some equation that can connect those variables, you're ready to go. Then you're going to differentiate both sides with respect to time, and you're going to, again, use that chain rule on there, because generally on this, time is not one of the variables that's involved in your equation. And then you're going to substitute in the known values. And it might be an actual quantity, and it might be a rate of change. But you solve for what's required. So that's kind of your step-by-step going through to do this. So we're going to just work through several examples now. Again, as I do this, as I said before, I'll put up, well, as I said on the last video, I'll put up the problem. I would pause the video, see if you can make sense out of it, and see if you can do it yourself. Then unpause the video and follow along with what I did and see if your work matched mine. And then if you think I made a mistake, then talk to me about it when we meet on our online meetings here. So let's get going. Air is being pumped into a balloon at a rate of 4.5 cubic feet per minute. Find the rate of change of the radius when the radius is 2 feet. We're going to assume the balloon is a sphere. And if you have forgotten the volume, whoops, don't want to go to that one yet. I'll go over here. The volume of a sphere is 4/3 pi r cubed. If you've forgotten that formula, you'll need that to do this problem. So let's take a look at this. What we know the radius equals 2 feet. We know it's being pumped into the balloon at cubic feet per minute. This is a volume, or this is a, well, this is per minute. This is a rate of change. It's a volume change, so this is a dV dt. So I gave you dV dt equals 4.5. And this is a constant rate coming in, so that's kind of nice. I don't have to worry about that, whether that affects based on R or not. What I need is dr dt. So the variables I have radius and I have volume. So that's why I need this formula right here. It connects the radius to the volume. So if I start with V equals 4/3 pi r cubed, I do my derivative, d dt, so I get dV dt, I got a constant, 4/3 pi, and then I have r, so that's going to give me, using the general power rule, that's 3r squared dr dt. And dr dt is what I want to know. dV dt is what I do know, and I know r, so I can plug all of those in. And I can get 4.5. Oh, this is nice. The 3's cancel. I don't have a fraction anymore. 4 pi r was 2 dr dt. So I can come along and say dr dt is going to be 4.5 divided by 16 pi, which is 0.090 feet per minute. This one's a pretty much nice, straightforward problem. Let's get it more interesting, right? An airplane. This kind of looks like a problem out of your trig book, doesn't it? Or pre-calculus? Airplanes flying at an altitude of 6 miles on a flight path that'll take it directly over a radar tracking station. The radar measures this distance s. It's decreasing at a rate of 400 miles per hour when s is 10 miles. What is the speed of the plane? So on this time we have this. Oh, we did that again. I have this rate of 400 miles per hour when s equals 10. I can't even say that's always the rate it's decreasing. It's just what it's decreasing at that time. So go ahead and try this one. Let's see, we're given the altitude is 6 miles. We're given that s equals 10 miles. And we're given ds dt equals 400 miles per hour. And we need to find the speed of the plane, which is dx dt, because x is the change in position here. So that's what we're given. That's what we need. Let's switch on to someplace else. Not yet there. Go here, here. I'll get used to this program eventually. Copy to whiteboard. There we go. So again, it might be useful to get that picture back for us. Oops, I need to go over here. So the picture here was x, here was 6, and this was my s. So my variables, I have s involved and I have x involved. So an equation that can relate those, since this is the right triangle, I can come along with s squared equals 6 squared plus x squared. And now we will come along and do our derivative with respect to time. And we have, clean that up again. S squared is going to be 2s ds dt. The derivative of 6 squared is going to be 0. I don't care. So I got 2x dx dt. And now I plug in my givens and see what I need to solve for. S, I know, is 10. ds dt, I know, is 400. X, I don't know x. So now comes, I'm going to need to come back to my original equation and say, well, when s equals 10, I have s squared equals 6 squared plus x squared. So 100 equals 36 plus x squared. So x squared equals 64. So x is going to equal 8. So I know now when s equals 10, x equals 8. So I can plug this into here. dx dt. And now it's just a little work to get this back into solve for dx dt. So here we got, what, 8,000 equals 16 dx dt. So dx dt is going to be 8,000 divided by 16, which should give us 500 miles per hour. So sometimes when we do this, we're given some information. We have to use another equation sometimes to find other information to plug in order to solve for what we need. So this is as it gets a little bit more complicated what we have to work with. New board here. Let's clear this off here. Go to our last problem here. So here we have a rocket launched, and the height is s equals 50t squared. S is the position above the ground measured in feet. T is in seconds. A camera, which is 2,000 feet from the base of the rocket, is recording the takeoff. We want the rate of change of the angle of elevation of the camera as the rocket lifts off. 10 seconds after liftoff. Give it a try. So we'll start off, what do we know? I'm going to start off with a picture. Here's my rocket, and it's going up this way to some height s. My lovely straight lines here. I think this has a smart Alec pen that'll make me make it straight, but I haven't played with it too much. Here's my angle, here's my camera. This is 2,000 feet. We're assuming it's going straight up, so to make things easier, we have a right angle there. We want t to equal 10 seconds. And we know s equals 50t squared. So that's what we know for this problem. So let's see what we can do with that. I'm going to want a little bit more room, I think, again. To the whiteboard we go. Yay! Okay, so we need d theta dt. So I need an equation involving theta. So when I look at this, it's a right triangle. Obvious one would be the tangent of theta equals opposite over adjacent. So there's my formula. I know something about s. I have some my theta here. I want d theta dt. Let's see where we can go from here. We can do this the hard way or the easy way. I'm going to try to do it the easy way. Let's see if it is. So I do my derivative. So my derivative of tangent is secant squared. And I have to take that times d theta dt, because we can't forget the chain rule there. My derivative of s over 2,000, that's going to be 2,000 times 1 over 2,000 times the derivative of s, which is just ds dt. Now here's the rub. What do I know? Do I know theta? No. I need d theta dt. I don't know that. I don't have ds dt. So I'm kind of out of luck on all bound. I'm going to have to do some more work on it. The one thing I am going to do is let's move this over to the other side. So in order to, I can divide by secant squared. Well, secant is 1 over cosine, so that would be the same thing as saying d theta over dt would be the cosine squared theta over 2000 times ds dt. So now let's start trying to find something. Let's start with ds dt, because I know s equals 50t squared. So ds dt equals 100t. So at t equals 10, ds dt equals 1000. So that's good. I got one of them. Now I have to find the cosine of squared of theta. So I'm going to come through, if I have a right triangle, if I could find s, I could solve for my hypotenuse, and then I could find the cosine from here, or I could if I really wanted to, use inverse trig functions to find the value and then plug it back in again. And yeah, that's for the birds, right? I know at t equals 10, s equals 50 times 10 squared, so s equals 5,000. So at that point, now I have, again, I'm going to say h squared is 2,000 squared plus 5,000 squared. So h squared is going to be, what? 25, 29. Oh, what a lovely number. And if I want to, I can take this down to, 5385. So now I have this triangle here. There's theta. There's 5,000. There's 5385. Here's 2,000. I need the cosine of theta. Cosine of theta is just going to be adjacent over hypotenuse. Cosine squared theta is just going to be the 2,000 squared over hypotenuse squared. Oh, I got that number here, 29. Ooh, doing weird things. So now I can plug that into here. So plugging all of this in together, I will get 2,000 squared over 2,000 times 29 million. Woo. Times ds dt is another 1,000. So brown looks good. I can cross out one of the 2,000s. 1,000 I can cross out some of that. I can take this by 1,000. I can cross out more of that. I end up with 2 over 29. Or approximately 0.069. And this unit is going to be in radians per second. One thing to remember we talked about before, I'm going to hit again. When you are dealing with calculus and the trig functions, you always need to be in radians. So you could do these other ways. There's other ways you can approach this. I did it this way because this kind of shows the idea of using other formulas to help find our things to plug in, because we're not always given exactly what we need, but we're given enough so that we can find what we need. Oh, here's another one to do. I forgot to do this one ahead of time. So, and I've already been at this for half an hour. So I'm going to stop. I'm not going to do this one for you. I want you to give this one a try. And then maybe when we get together on one of our class together, we can talk and see if you got this figured out, or if there's questions. If we need to go through this, we'll go through this at that time. But I'm going to give you straight to the homework here. You've been listening to me enough. So work on this. Bring back your questions. That crankshaft one is a good one to go over, but I don't want to take up your time right now. So we will do that in class when we're talking together about that. Have a good afternoon.